Hello बच्चों, this is the video lecture number 8 of the unit Electrostatics, and in today's lecture we will study the third application of Gauss theorem, which is electric field intensity at a point due to uniformly charged thin spherical shell. In this topic we will study 3 points. First is the electric field intensity at a point outside the shell. Second is the electric field intensity at a point on the surface of the shell. And third is the electric field intensity at a point inside the shell. The third application of Gauss law is electric field due to uniformly charged thin spherical shell. In this topic, to find out the electric field intensity at a point near the spherical shell, let us consider a thin spherical shell having continuous charge distribution over the surface of the shell. And let R is the radius of the shell having center at O, plus Q is the continuous charge distribution over the surface of the shell. P is the point near the shell at which we have to find out the electric field intensity. R is the distance between center and the point of observation P. E is the electric field intensity due to the surface charge distribution over the surface of the shell. We will consider a small area element at point P to find out the electric field intensity, and the area of that small area element is dA, and the area vector is vector dA. So the first topic is electric field intensity at a point outside the shell. In this case, the distance of point of observation P from the center of the spherical shell O will be greater than the radius of the shell. For this, let us draw a Gaussian surface through point P in such a way that electric field intensity at each point of the Gaussian surface is same. Now we can write out the value of flux phi is equal to closed integral E dot dA. Here in the diagram we can see that the angle between E and dA is 0 degree. Therefore, the value of cos 0 degree will be equal to 1. Hence we get phi is equal to E closed integral dA. In this expression, electric field intensity E will be out of the integration because the value of E is same at all the points of the Gaussian surface. So after integrating dA over the whole surface, we get flux phi is equal to E into 4 pi r square. Here 4 pi r square is the total surface area of the sphere. Now using Gauss law we can write the expression of flux phi is equal to closed integral E dot dA is equal to Q by epsilon naught. By putting the value from equation 2 in equation 1, we get Q by epsilon naught is equal to E into 4 pi r square. From this equation, we will get the value of electric field, which is E is equal to Q by 4 pi r square epsilon naught. Here from this equation, equation number 3, we can observe that electric field is inversely proportional to r square. Hence it is clear that the electric field intensity at any point outside the spherical shell is in such a way that the entire charge is concentrated at the center of the shell, not on the surface of the shell. Now we can use the continuous surface charge distribution on the Gaussian surface, and we can write the expression of charge in the terms of surface charge density, which is Q is equal to sigma into 4 pi r square. By putting the value of Q in equation number 3, we will get a relation between electric field intensity and surface charge density, which is E is equal to sigma by epsilon naught. The next point is electric field intensity at a point on the surface of the shell. In this case, the point of observation will lie on the surface of the shell. Therefore, small r will be equal to capital R. Now we are going to draw the Gaussian surface through P, which will lie on the surface of the spherical shell as shown in figure. So, as we have done in the previous point, the electric field intensity using equation number 3, we can write E is equal to Q by 4 pi epsilon naught R square. And the same thing is E is directly proportional to 1 by R square, and E is equal to sigma by epsilon naught. Third is electric field intensity at a point inside the shell. In this case, the distance of point of observation from the center of the shell will be less than the radius of the shell. Now, by drawing the Gaussian surface through point P in such a way that the electric field intensity at all the point should be same. So, it is a sphere of radius small r inside the shell. So, total flux can be written as phi is equal to closed integral E dot dA is equal to Q by epsilon naught. Here, there is no charge inside the Gaussian surface, so we can write the charge enclosed by the Gaussian surface is equal to 0. Hence, flux will be equal to 0, and therefore electric field intensity inside the spherical shell is equal to 0. We can show the variation of electric field intensity with a small r, which is the distance of the point of observation from the center of the spherical shell. As we have got the value of electric field intensity in all the three cases, so for r is equal to 0 to r is equal to capital R, the electric field intensity will be 0 as shown in figure. There is no variation. At r is equal to r, the electric field intensity is maximum, as we have studied in point 2 of the topic. After that, that is when we will go outside the spherical shell, in case r is greater than capital R, the electric field intensity will be inversely proportional to square of small r, as we have studied in first topic of today's lecture. Your homework is learn the derivation and graph of this lecture and derive Coulomb's law from Gauss law on the same concept which we have done today, and revise all the topics of this lecture thoroughly, because I am going to start numericals from the next lecture. Thank you.